Okay, so welcome to the conversation series on scalable interaction paradigms for pervasive computing environments. So together with Heiko Müller, I'm hosting this conversation series on behalf of the entire priority program, which is a large DOG-funded project with many exciting German HCI labs being involved. And every week we are presenting one international guest that very much relates in his or her work to our projects. So today I have the pleasure of running this with Jürgen Steinle, and also I think Jan Borchers is present today. And we are very happy to have Stefanie Mueller here. I think I know her many years. I'm excited. I remember your early work on laser origami. I think we met and we looked at the materials and the results. It was really exciting, and this is some years ago, and since then you made an excellent career, and Jürgen will introduce you to the audience a little bit more deeper.
Yeah, thanks, Susanne, and welcome, Stefanie. It's a really great pleasure having you here. Stefanie is, as we see on the slide, an associate professor at MIT in the EECS department, where she directs the engineering group at CSAIL. She holds a PhD from Hasso-Plattner Institute, where she has worked with Patrick Baudisch, and I'm sure you have met Stefanie before or heard about her because she's really active in the community. She's held many different chairing positions, served on so many different committees. Just to pick a few examples, Stefanie has been a program chair at WIST, and I think, if I'm well informed, will be the paper chair of next year's CHI in 2023. So we're really excited to have Stefanie here today because she's very well known for her work in personal fabrication, and this relates very well to some of the research we're doing on the SPP. So I think one interesting aspect of Stefanie is that in her work on personal fabrication, she's like always combining fabrication with novel tools. She's engineering and with some really innovative approaches of using materials. And she's made so many important contributions that I think I should not list them. The list is getting too long, and you will see some of her work presented in a few minutes. I think work that clearly stands out is work she has done in her PhD and in following years on speeding up prototyping with digital fabrication, so people can prototype objects and functional devices with 3D printers and laser cutters in very, very interesting and innovative ways. Stefanie is also working on metamaterials, where you use, if you will, classical materials in digital fabrication, but orchestrate them and lay them out in interesting geometries to conceive new functionality. And then maybe most related to the work that we're doing in the Rhine project here in the SPP is using new materials for advanced functionality, where Stefanie has intensely worked on, for instance, customizing colors and visual textures of objects by using new materials, on embedding electronics, with printed electronics, or more recently, even how we can dynamically adjust fabrication parameters to printing materials. So there is many perspectives on materials and fabrication that Stefanie can share and will certainly share today. And I think we should get started with her talk on giving physical objects digital capabilities, and then we'll have plenty of time for conversation with Stefanie. So please, Stefanie, I will just hand over directly to you, and please take it away.
Okay, wonderful. Thank you so much for the introduction, Jürgen and Susanne. Very nice to see everyone. And although I was introduced as an international speaker, as you can hear by my accent, I'm also German. So it's always nice to talk with the German HCI community. All right, so I brought a bunch of projects for you today as an introduction for, for my lab's vision, where we try to give physical objects digital capabilities. And I really just want to use this talk to show you a bunch of examples, and then we can go into the conversation. I will also try to give some technical details for the projects, but I may cut it here and there just in the interest of time and not to overload you. All right, so if you're a little older, depends on how old you are, you have seen that computing has quite changed a lot in the last decades of what we do, how we do different things today, right? So I remember when I was a teenager, for instance, right, there was no Wi-Fi. You would have to use a cable to, route to your computer to actually access the internet, which today seems like pretty ridiculous for most people, right? And there were no mobile phones. So one example I love to use here also for physical objects is that changing appearance, for instance, was super easy today, right? Because of all the digital developments we have. So let's say you're a product designer and you want to design this car here. It's super easy in digital. You just click one button and then the car is blue or yellow, right? And you don't have to wait for a long time or have a lot of effort. But in physical, we're actually not quite there yet, right? So let's say if you want to change your car in physical, right, you would actually have to maybe bring it to a garage. They would spray paint it over a day. It would be very, very expensive, right? So it's definitely not as easy in physical today as it is in digital. And my lab is really working on the question, can we make it as easy as in digital, and how would we go about this? And I will dive right in and show you like one example how we give such physical objects, like these digital capabilities of like an update function for appearance, for instance. So my lab has developed this like smart material that you can spray onto objects. And then if you project light of a certain wavelength on it, you can actually change the appearance of the object. So you see on the top right corner, it's not quite instant as in digital, but it's pretty fast, for physical object, frames. And you can see we can do this on like 3D objects. We can do this on like 2D surfaces, like a phone case, for instance. We can do this on textiles. So you could imagine maybe updating your shoes on a daily basis or even hourly basis, right? And if we had a larger projection setup, we could also do this on cars. If you imagine like a car sharing scenario where every customer can customize the car before they use it, that would also be cool. This is just like a little model car that fits into our projection setup. So it's not a full size object. So just to show you one more time, these are, for instance, like 3 different appearances we made on the same phone case. So literally you can just apply them as a texture and then transfer them with our smart projection system. And, I showed you lots of small scale examples, but you can also imagine this maybe on a room scale, right? Because our material is literally just something you can spray, or you can even paint it on a wall. And if you imagine having some sort of projection system on the ceiling, you could maybe even leave your office and you're like, I want my home to look like this tonight. And then maybe the walls could update or the couch could update and stuff like this. And you come home every day to basically a new place that fits your mood. So I want to give you like a few details for how this works. This is probably the most technical info I will give today. And then for all the other projects, I will cut it much shorter, but I thought it's worth explaining a bit of the background. So we use these special materials. They're called photochromic dyes. And as you see, by default, they are transparent. But then if you shine some UV light on them, they actually switch from transparent to being colored. So now you can use them in the normal environment, but you can also just fade them out back again to transparent by shining, a high intensity visible light on it. So you see, now they go from being colored back to being transparent. So here you see the summarize one more time, from transparent to colored, you shine some UV light to saturate the dyes. And then to make them transparent again, you shine some visible light, like RGB light, for instance. So this is kind of cool. Those materials exist. You can buy them. We just bought them from a company in Japan. But the problem is they only exist in a single color. So you can buy them transparent to cyan or transparent to magenta or transparent to yellow. But really, if you just used one of these dyes, all you would be able to do is to do like one color images. So the question remains, how do we actually do these multicolor things, right? And it's actually, very similar to what you probably know from the 2D printing process. So if you have an inkjet printer at home, right, it has cyan, magenta, and yellow in the little inkjet dye cartridge. And then what the printer does is it basically mixes them together to create any of the different colors, right? So if you print them all together or mix them all together, you get black, as you can see on the right side. So how can we know that, let's say we mix the cyan, magenta, and the yellow all together in a single bottle? All the colors are somewhere in this black color included, but how do we actually create those? And you can see an example on the right side. Again, this is the same bottle and all the images with the same liquid. And let's say to go from black to red, what we would have to do is that we have to make the cyan dye in this bottle transparent, because if cyan is transparent to the eye, all your eye sees is magenta and yellow, so you get the red color, right? And the same for the green color. If you want to make green, right, you would have to find a way to make the magenta in the bottle transparent, so your eye only sees cyan and yellow and you get green. So far so good, but how do we actually make a single one of these dyes transparent in this bottle, right? How do we do this? And this is like the last technical bit for this project, is you need to know a bit about the optics. So what you see here is on the bottom are the different wavelengths of light that we will shine onto the dyes. And then on the y-axis, you see how much each dye absorbs a specific wavelength. So you can see that although all the colors are in this one bottle, the cyan actually has a different peak absorption than the magenta and then the yellow. So what this means is if we shine some light, let's say at this wavelength, onto the black liquid in the bottle, only the cyan would get transparent. So as I said, once the cyan gets transparent, right, we only see the magenta and the yellow, and you would get the red color, right? If you have a different light source for magenta and yellow, you can deactivate each of those individually. So where do we get these three light sources from? Actually, if you have a normal office projector, like you would use for normally projecting the slides, I know I'm not physically there, but just imagine we had an office projector on the ceiling. They already have three light sources. They have a red, green, and blue LED. And lucky for us, they are at the correct wavelengths, as you can see here. So literally all we do is what you see here in this video, we shine a combination of red, green, and blue light onto our smart material to go from the black color that we initially spray on the object down to any of the target colors. So there's lots of like optimization algorithm behind this, but I spare you the details. We'd rather show you a bunch of other projects as well. And just, you know, to like, since this is like the smart material talk here more or less, right? I also want to show you it's actually very simple. So all we do is we buy these dyes from the manufacturer and then we just mix them here in an automotive lacquer from the hardware store. So we literally just take this powder that is color changing, mix it in the lacquer, mix everything together. Then we have these three different vials here with the individual colors, and then we just pour everything together to make our black dye. And that's literally all we load in our airbrush can, and then we can airbrush it onto any surface that we like. Okay. So that was one example of how we can create reprogrammable appearances. I will show you two more examples in this category, and I will keep it a little shorter for how these things work. So this is a project we currently have under submission, so it's not yet published, that uses a birefringent material and polarizers to create different appearances. So as you can see here, as we rotate a part of the object, we can actually make a color change happen here. So what do we need for this? Again, it's about materials. So we need a material that has a birefringent property. And again, I spare you the details, but it basically means that under polarized light, those exhibit different colors. And one material that is birefringent is, for instance, cellophane. So, you know, if you wrap your food and stuff, that's something you can already use. And then the only other thing you need is a polarizing sheet. You can also buy it from Amazon, costs like $12, and you're ready to go to create your color changing objects. So here's a bit how this works. So you need two polarizer, like we call one analyzer and one polarizer, but they're really the same thing. So it's two of these like black polarizer sheets, and you put your cellophane in the middle. And then if you rotate the cellophane will actually go from transparent to being opaque and more opaque as you rotate it. So I hope you can see this here in the annotation. It's going from 0 degrees to 20, 45. And then at 90 degrees, it has the highest saturation. Mm. If you would keep rotating here, it would get transparent actually again until it gets like colored later. So every 90 degrees, it basically goes from transparent to colored. If you want to make different colors in the mosaic, you just have to stack multiple layers of cellophane. So the thicker the cellophane, the more the different the color is. So if you just put one layer, you get a blue. If you stack two layers, you get an orange, and so on. So just by layering more cellophane on top of each other, you can make different colors. And then to fade in and fade out different appearances, what we do is like a simple trick. So if the cellophane is in alignment with the polarizers, it will be transparent. So if you look on the left side, we only see the mosaic A pattern here because it's at 45 degrees. But we do not see the mosaic B because it's aligned with the polarizers. Versus on the right side, it's different, right? So the mosaic A is being further rotated, so it starts to disappear, but the mosaic B is now at 45 degrees invisible. So simply by like smartly rotating those things with respect to each other, we can transition in and out between different appearances. This is what you saw here, like we rotate 45 degrees and one mosaic goes out of the view and the other one becomes visible. So this is how we do these transitions. And we have a few more applications here. This is like I know it's not the hottest topic right now, but COVID visualization, where you can actually see where the cases are increasing in the US. And again, you can see as we rotate further, the colors change in the visualization. Okay, so the last way for like just changing appearances in like a programmable way is not using materials, but to use lenses for an optical effect. So I put a Christmas card here because almost Christmas, and I'm sure you have seen those cards when you go to like the supermarket or to a gift store, where if you look at the card from different angles, you actually see different things. So this is super cool, right? But we have only seen this in 2D so far. So the way these cards work is that basically the entire sheet here is covered with teeny tiny lenses, like all over. There's like thousands and thousands of tiny lenses. And underneath each lens, there are different color dots based on the images. So if you look at the lens, for instance, from the left side, because of the magnifying effect of the lens, you only see the blue dot. But if you look from the right side, you would see, for instance, only the red dot. So this is basically how this is done. There's all of these lenses and they all have like different colored dots underneath. And depending on how you hold it, you either see, let's say, more blue dots because there's more blue background, or you see more green dots because it's like tilted towards you. So this is cool. We have it in 2D, and we were asking ourselves if like 3D printers and their new capabilities to also print transparent materials for the lenses and to print full color patterns. Can we actually print a lenticular object, like these color changing, appearance angle changing objects in 3D as well? And the answer is yes, it's possible. So here you see, for instance, one object that we 3D printed on a pretty high-end 3D printer. It's printed in one piece. So as I said, like the printer can print clear material for all the lenses, can print full color resolution underneath, and then also can print like regular material. So the idea here was this is an airport case, and maybe when you drop it to the floor, it would kind of like flicker because the angle towards your eye changes as it falls down, so you notice and you can pick it up. This is one of my favorite examples. This is a kettlebell. I hope it's playing. And depending on how you hold it, it will show you should hold it higher, you're holding it at the right height, or you're holding it too high, so you actually do your exercise correctly. And this is also a cute example from my PhD student, Winnie, who did this. This is a nightstand lamp. And when you lay down, it shows you good night. But when you stand up, it shows good day. So I know it's very pixelated here because the print resolution is not great, but I hope you see the good night and the good day based on the viewing angle as well. And this is the last example I want to show for this. This is a shoe. If you ever need a positive message, so if you look down on your shoe, you see cheer up, but everybody else who looks from the side will just see like a normal shoe that looks like gray and nothing special. So it's kind of like, can give you like a positive reinforcement message. Okay, so I talked a lot about, this theme of giving the physical objects digital capabilities. And the first thing was just like updating appearances as easily as we can do in digital, right? In digital, we can use an editor, just click one button, color is changed. The same when we take photos, we can apply a filter, it changes right away. Can we do the same for physical as well? So the second topic I want to briefly show is how to just sense more interaction in the physical environment. So for instance, if we are on a computer, right, every click we make, the digital environment knows what did we click, where did we interact, and reacts to it in some way, right? But in the physical environment, right, my chair doesn't know I'm sitting on this chair, my desk doesn't know I'm using it right now. So can we somehow augment physical objects with these sense-making capabilities that we already have in digital? I will show two projects here briefly. This is a project we call sprayable user interfaces. What we do here is we just load a conductive copper ink into a spray gun, and then we can spray, for instance, sliders or touch buttons onto walls and other objects. So here you see, for instance, 2 slider segments. And on top of these slider segments, we can also spray some color if you want to cover it up and make it more beautiful. And then in the end, we sprayed this user interface here where you can use this like touch button, for instance, on the wall to turn on your lamp. And then these sliders can, for instance, be used to set the brightness of the lamp, also the color. And again, this just took us, a few hours of spray time, and you can basically augment your home with like new user interface elements simply by spraying these conductive touch elements. So what I always love about the research we do is it's actually pretty doable, right? If you want to replicate it. So all you need to do is you have to buy this like copper paint here from this company called Luminor, and then you can spray all of these different elements that I showed on the side. So this was an example that I showed you that is 2D on a wall, right? But we also want to see, can we actually augment 3D objects in an invisible way? And for this, we found this other cool material. It's called P.PSS. It's also conductive, but it's actually clear and you can't really see it when you put it on objects. So what we did here is we sprayed on a couch in our lab space a bunch of touch buttons on the armrest, for instance, and also some buttons on the backrest. So we can actually see if a user is sitting down and leaning backwards. So we sprayed this, you see it's conductive, but once it's dried, it's really hard to see. So here's, for instance, our augmented couch. Again, we can detect if a user is sitting down. So here in this case, we load a photo album as an application, and then the user can like swipe left and right on this like smart furniture. And this is a very simple example here, but you could imagine if the entire couch was augmented with these touch sensors, we could do like full pose detection, for instance, to really reason about what is the user doing in the environment. So we have like a nice user interface for this as well. You can like sketch out, what you want to spray, and then we either generate you some stencils that you can laser cut, or you get like a projection mapping done, so you actually know where you have to like spray all the buttons and the sensing elements. Yeah, I just want to show you this here as another fun example. We actually sprayed on our lab space. I'm not sure if it's allowed, but we just did it. And this is like a music interface where it's connected to Spotify. So when you touch the notes, you can actually play different like Spotify playlists in the lab space, which is like lots of fun. Okay. Cool. So in the interest of time, I'll just briefly show you the second project. So I showed you how we can augment surfaces, right? We can spray on surfaces and add like touch capabilities, or like hover sensors and sliders. But can we also integrate sensing inside the structure of objects? So for instance, if you sit down on your couch, right, can we actually really detect the deformation in your couch pillow to really get like a full reconstruction of what you're doing? So for this, we developed this new technique where we can actually integrate sensing into something that's called like mechanical metamaterials. So you can see here, for instance, these are conductive 3D printed walls on this side and this side. And as we move the joystick, the distance between these walls changes. And this is what we can use to sense, for instance, here, like the direction in this Pac-Man game. Yeah, here I have a close-up for you to see. This is the joystick in like small, again, printed in one piece. And we have these conductive walls on each side, which basically act as an electrode. And as you push towards the right, the distance increases, so the capacitance decreases. And if you do the opposite, right, the capacitance actually increases, so we can make sense of these interactions. Here you see this one more time. You see how the conductive walls get closer to each other, and we can accurately sense this and replicate this in digital as well. And again, it's very doable, right? All you need is a dual materials 3D printer, some conductive filament, and some flexible filament. And once you have this, you can print these types of objects, and you have something with sensing integrated in the structure through these conductive cell walls. So here's another example. This is a music controller. So you can just like push on the different buttons and measure the deformation. You see it in digital mirrored there. And then we can also create like other types of sensors like accelerometers, for instance. And again, the same principle applies here. We just measure how far are the conductive walls away from each other. You can do like rotational elements as well. So, you know, this project really just shows the sensing principle in like very small objects. But what I would hope we will have in the future is that actually like full objects are created from these mechanical metamaterials, and the sensing is directly integrated into the cell structure. Okay, so the third example I want to give for, you know, giving physical objects more digital capabilities is, can we actually add more metadata? Right, so for instance, if you click on a digital file, you do like a command I, right? You get like, oh, how big is the file? Who made it? When was it made? You get all of this extra information. But for physical objects, except if there's like an ugly, you know, QR code attached to it, we don't really have that yet. So I showed just a few projects. Again, these have not been published yet, so this is like early work. Here's one example of how we were planning to do this. So for instance, if we laser cut finger joints on objects in different thicknesses, can we, for instance, encode bits into these objects? So a shorter finger joint could be a 1, and the longer finger joint, for instance, could be a 0, which means when you take a photo of the object, you can actually process this code and extract some information from it. So you can see this here on the app on the phone, for instance. I'll just play the video. So you can see here, basically, we take the standard laser cut object you would input into our system, and then we modify the length, for instance, of the finger joints, or we can also do like living hinge adjustments as well. And then what you can do with this, for instance, is, let's say you want to figure out like where does this object come from. You can just take a photo, and then you can say open, and it's going to actually get you to, let's say, the Thingiverse page or wherever the chair was made from. Here's another example of how we can embed information in 3D objects. Let me play this one more time. So you see, this is what you see with the naked eye, and this is what you actually see with the infrared camera. And we can embed these markers by 3D printing them with an infrared filament. So if you 3D print with an infrared filament, again, you as a user, you will not notice that there's actually an augmented object. But if you look at it with your phone, if your phone has an infrared camera, otherwise you can get like a little add-on, your phone can actually see the marker underneath the surface of the object. And there's a bunch of cool things you can do with this. Here's some IoT applications. Let's say in this case, we take a photo here. This is a loudspeaker, and you can just adjust the volume immediately. So you don't have to, like, you know, connect to the device in some other way. Here you take a photo of the thermostat. Again, there's like a QR code underneath, right? And you can adjust the temperature. And then let's say this here is like let's say you go to an Airbnb and you have to log into the Wi-Fi, right? This is like a little Wi-Fi station. And when you take a photo, again, it gives you like the, you know, the Wi-Fi name, and then you take another photo to get the password from the bottom. Okay. And this is the last project I want to show, in the sense of just like augmenting physical objects in a way that is like unobtrusive, but still gives you like a lot of meta information. This is something we published at Kai a while ago, where we actually modify the slicing parameters when you 3D print an object. So for instance, if you 3D print an object, you slice it and you just change a setting like print angle, you can actually create each copy at a slightly different way. So you see these are little key covers you can attach to your key, but one is printed at 120 degrees angle, one at 30 and one at 65. And now if you actually take a photo of these keys, our computer vision pipeline can extract these slight changes in slicing parameters and can identify, you know, this was, let's say, you know, Jan's key or Jürgen's key, right? Okay, great. So here's one application for this. You can also do infill parameters, for instance, if you have a light source. So in this case here, we detect, you know, whose coffee is this, and then we pour your coffee without you having to select anything. Okay, good. Okay, so this is the last part I will show, and then I will wrap it up so we can have a bit of a discussion. So we were also super interested, can we somehow make it happen that we can make like fully functional objects right off the print bed that could act in the real world immediately? So today you can already 3D print like passive objects, right? You print something, but it can't really do anything because it's just, just a piece of plastic, basically. So we did a bit of a crazy engineering project. Our goal was, can we make a quadcopter that we can kind of like print out right away and that could fly out of the fabrication bed immediately? And to make this happen, we augmented a laser cutter with a pick and place mechanism. So we have a little storage for different electronic components on the right side. And we just pick and place them, and we have a silver extruder for making the conductive traces. So I hope you can see this. It's a little difficult in the video, but we're basically laser cutting the shape first. Then we use our silver extruder to extrude the conductive traces. So at this point, they are not yet conductive. They are just like uncured silver. So now we have the traces ready. We go to the site where we have the electronic components and we just pick and place them. So you see, we will bring in the rotor blades, and then we will also pick and place the microcontroller for the middle of the quadcopter. And then, as I said, like the silver is not yet cured, so we actually have to apply some heat, and we also use the laser again for heat curing the silver. So we cure everything together. And you will see once the laser is done curing the silver traces, there will be a blue light coming on, and the quadcopter can actually fly right out of the fabrication device. It's coming on. And now the rotors are going, and then it's like, whoop, and it's going away. All right, so yeah, I have a bit more detail here on the hardware, but I will just wrap it up here. No? So this is the add-on for the laser cutter we built. Okay, so let's zoom out. Computing really has changed how we do many things today, right? And I think the older you are, the more perspective you have on this. However, with in physical, we don't really have these capabilities yet, right? So how can we create them? And I showed 4 different examples here, one on reprogrammable appearances, so we can change the visuals really quickly, how to add more sensing to our physical environments, how we can embed metadata into physical objects. And then I gave like a brief outlook how we can actually make like fully functional things that can act, like be fabricated and act in the real world without even a user being involved. So with this, I want to thank all of my students. Really amazing work, right? Without them, none of this would have been possible. I'm always really impressed also by all their creative skills, and also technical engineering skills is really amazing. And then I also want to thank all the sponsors for our research projects. So with this, I will wrap it up and we can have a conversation, hopefully. Thank you.
Yes, thank you very much. And you hear there's digital applause. It should connect to a loudspeaker on your side and then make a huge applause sound on the physical object where you are. Good, great, that was excellent. I have a large number of questions, so let's maybe together with Jan and Jürgen jump into some of them until the audience warms up also for their questions. So as you've seen, we are really looking into the question, as you said, sort of bringing rich interactive material into everyday spaces. That could be the couch and the table. So when you use such novel material for your interfaces, let's say the spraying, how does it then come to the point of, let's say, the sensation granularity? What is the pressure that actually works? What is the reach I can have with the hand? Is it able enough to really detect it? How is the error rate? So how far do you go with that? Because of course, at some point it is highly exciting. So that is awesome what you are doing here. So how you then transition into the question, does the material actually need to be revisited at some point to have a, let's say, better sensation of a swipe movement? So how far do you go, and would you then iterate over the materials or even find companies that do even better materials?
I love the question. It's such a good point. And it's a great point for opportunities, also a great point of pain in my group. So I would say you totally have it spot on, right? Let's say if you just take the sprayable materials, right? Like the entire pipeline influences what can be done and what can't be done, right? So let's say the material itself has certain particle sizes, which limits how fine-grained the spray can be, right? Like if you spray with it, because if you have a too small nozzle, right, everything will clog. But obviously you want to have it as precise as possible because you want to have like really fine sensing capabilities, right? And then further down the line, right, like how good is your sensing, right? Do you need some machine learning to actually, contextualize over all the data, right? And how far can you push it? So I think it's a really interesting question, how much of this entire pipeline do you consider, and where do you say, like, this is my expertise, I cut it here, and I hope somebody else will pick it up. I think we are always trying to push it as far, I would say, to like the left side, the hardware and the material optimization. But I don't want to just say this is the only solution, because I think a lot can also be done just on the sensing and improving the processing of the signals. So for like, how far do we go? So we definitely often build our own like fabrication devices to try to bypass some of the limits that current fabrication devices have. And even for materials, we have a wet lab here. We often try, let's say there's like, can the particles be further broken down, or can they be more dissolved, right? We try to do our own material mixing. But since in the end, like 99% of people in my lab are still computer scientists, there's like a certain limit to where it just becomes like randomly playing around with stuff and hoping for the best. So we actually try to reach out a lot to material scientists. Sometimes we get lucky and we actually get a really good insight, but very often we just get stuck in that space. And I'm sure like Jürgen has the same experience with the inkjet printing and the clock nozzles, and can you optimize the materials? And I'm sure there's so much more we could do if we had like a bit more material science knowledge in HCI, but that's definitely something where, right now we are just, I feel like at least in my group, we are still just like reading around and, trying to learn something on the fly. I'm not sure if somebody else wants to share on this topic.
Yeah, it looks like Jürgen is just on his way to come.
I wanted to directly follow up on this. I think this is a very interesting point. As you just mentioned, Stefanie, I think scalability, if you will, is one of the pain points of where we're currently standing in fabrication of interactivity. And it happens to be the theme of this overall SPP. So I think this is also like a good match. I think that in terms of input, we're doing fairly well, right? Both in terms of the resolution of input and also in the scalability and the granularity. But I see many challenges ahead in terms of how we can scale up visual output and also shape-changing output. And I myself sort of also have difficult time seeing how we can move forward and if we should move forward. One way of looking at this, and I think sort of the example that you gave about the wallpaper resonated with me in the sense that you said people can update their wallpaper once a day or once an hour. And we look at, if you look at the granularity of the updates, this is of course much slower than the high frame rate interactive updates that you would have in common touchscreen devices. And I think it's for a good purpose, because objects in the physical environments are different than touchscreen displays. So I was curious to hear your take on this question from an interaction point of view, sort of how far do we have to go and how far should we go in increasing the resolution and the frame rate of updates? And to what extent is maybe just right to consider objects and real world surfaces in a different way than classical touchscreen interfaces?
Hi, that's a very good question as well. Maybe I'm a bit on the extreme side. I actually do think the physical object should have the same resolution as the digital, because why not, right? Like why should my, if my wall should be like a giant display, why should it not have the same resolution as, like a digital small display, right? I think that would be great. The other question is like, is it always necessary? I think that depends very much on the use case specifically, right? same as in digital, not everything has to be like over polished, right? It really depends. Are you, prototyping something or just trying something out, right? Or is it like the final version? Yeah, I think that's maybe I hear like when you're young, you're very extreme. You're like, everything has to be perfect and exactly the same, right? So I'm not sure if I will soften a bit on this viewpoint later, but right now it would be great if in physical everything would be the same as in digital in terms of ease of, change and manipulation.
Yeah, Jan.
Yeah, hey, Stefanie, hi, and thank you so much. That was a great whirlwind of a presentation. Lots of very cool stuff you collected for us, and thanks for sharing some work